Thanks everyone for coming back from lunch, and we'll start again the second part of our summer school here. So the first talk will be given by Josh Robinson from Penn State University on 2D material growth.
Thanks a lot, Steve. So Steve came over and he made sure that I knew that I couldn't have any more than 75 minutes. Yeah, so as introduced, I'm Joshua Robinson from Penn State University. Wear a few hats at the university related to 2D materials in a couple of different centers. The one that most probably closely relates to this workshop is the 2D Crystal Consortium. So it's actually a user facility. It is not just a center. The user facility there is focused on growth of 2D materials. So we have a couple of MOCVD systems, a couple of MBE systems, all of which have a variety of in situ characterization techniques that are tacked onto them. This is like a national user facility. So if you were to go to any of the national user facilities, you write a 2 or 3 page proposal. And if it's reasonable, then we accept it, and we can either just send you samples, or you can come and learn about 2D materials growth via MOCVD, chemical vapor transport, like we heard earlier today, as well as MBE, and then there's ARPES, STM, and a whole variety of other things that are in situ. So that's my advertisement for that. If you want to hear more, there's more here at mri.psu.edu. So that's the Materials Research Institute, which is housed in the Millennium Science Complex, also affectionately known as the Millennium Falcon. All right, so we've heard a lot about 2D already. You're going to hear a lot more about 2D this afternoon. This is my 2D tree, or tree of 2D. It all started with a strong foundation in graphene, and then rapidly branched out into a variety of different layered materials, of which you've heard most about today are the chalcogenides, but there's maxenes, monoelemental, nitrides, oxides, etc. The reason you hear mostly about these guys now is because just within this layered family of materials, you've got a huge variety of chemistries across the palette here. And I think overall within 2D materials there's over 2,500 or something like that now predicted to be stable that you can make, which will keep scientists very busy, and it ultimately boils down to probably 1 or 2 of them will be useful for industry. But it's transition metal dichalcogenides, group 3s, group 4s, and group 5s, which are topological insulators. So you've got this whole host of materials that you can make. The key is well, okay, how do we make them? And in this particular case, we've heard a lot about the bulk crystal growth this morning, which is fantastic. I enjoyed the talk. And there's also this chemical exfoliation where you can go to a mine, dig it up, brush the dirt off, and win a Nobel Prize. And some other processes as well. The 2 that we typically use are what I refer to as powder vaporization. It's also known as CVD, or solid source CVD. So this is where you take your powders, you put them in the tube, and you grow material, 2D materials from that. And I have one slide basically talking about this. It's not the most uniform or reproducible technique, but it is a low cost of entry technique, which is why there can be 5,000 papers a year now published on 2D materials. We use more traditional CVD as well, metal-organic chemical vapor deposition in our techniques, but both of these are quite useful for exploring properties in these 2D materials. So that's why I kind of look at these as 2 techniques to help us understand thin film versions of these as you grow them on a substrate. So related to powder vaporization, people have been doing this for 10 years now in terms of this process. You basically have, this is an example for MOS2. You have sulfur slightly outside your furnace, whether it's another furnace or a heat tape or something, it's typically at lower temperatures. And then you have a metal oxide that's inside. Very standard setup here, you flow argon in. What you typically find is if you look at the partial pressure of your molybdenum oxide in this case, but it's the same for all of your transition metal oxides, you'll find that the partial pressure very near the source of the moly oxide is very high. That's the stuff in red. And then you also see where it can tail off and it comes down here. Now this is a 4-inch tube, 100 millimeters, right? So you can see that it's quite non-uniform up close. The problem is the ideal partial pressure for the moly oxide or the metal oxide is in that arc shown right there. So in this little orange place here. Everything down here, you get very little to no nucleation. Everything up here, you get giant amounts of molybdenum oxide coming off. You end up with a sample that kind of looks like this. And in fact, this is this thick MOS2 and MOO2 that's shown in here. And you get monolayer films and kind of this arc around the sample shown here. And then submonolayer up here where you can get your individual triangles, et cetera. Now you can play games and you can make it more uniform by tuning the position and those kind of things, or flipping the sample here upside down and you can get it more uniform. But for the most part, this is what I would refer to as a finicky CVD approach. So within my group, we focus on a variety of different 2D materials, a lot on growth, a lot on properties. Our goal really is to grow the materials so we can understand the properties of those materials. A variety of different flavors of graphene, 2D metals and insulators, and this is with a new technique that we're working on now. A variety of different chalcogenides, 2D allotropes, and heterogeneous systems, so sticking them all together. I'm not going to go over everything, but what I want to focus on today is looking at epitaxy of these 2D materials. Of course, it is supposed to be a talk about growth. Understanding these property correlations. Just because PL is phenomenal doesn't mean anything else is. Growing with salts, so there's a lot of new hype in salt-assisted growth. Doping these 2D materials, meaning substitutional doping of the 2D materials, and some novel growth processes, which is basically this guy up here. I affectionately refer to it, confinement heteroepitaxy, as CHet. My students don't necessarily like that, but that's okay. All right, so epitaxy, toward wafer-scale 2D single crystals. So before we even get to the point of growing epitaxial layers, meaning things that are oriented with respect to the substrate, there's a couple of little things that I want to bring out, and that is your precursors really matter. Now this is in MOCVD. It's the same in powder vaporization with the metal oxides, etc. But the example that I have here, so this is MOCVD. We're going to grow tungsten diselenide on sapphire. Here you can do, this is just a 1 centimeter square. It's very uniform across the whole surface. We can make mono, bi, tri-layer, what have you, on these samples. Our tungsten precursors, tungsten hexacarbonyl, and we can either use dimethyl selenide or hydrogen selenide in this particular case. And what we find, depending on which precursor we use, is that the carbon content in our film can be dramatically different. So in the blue and green here is bare sapphire and WSE2 grown with hydrogen selenide. They pretty much overlap each other. But when you use dimethyl selenium, you see that the carbon peak is dramatically higher. Actually, in this particular case, you get a reduction in the carbon peak for the hydrogen selenide. So we've got some smudge on the surface, right? When we have our wafer, if we have, depending on the precursor we use, we can either reduce the carbon contamination on the surface or we enhance it. And presumably it's because of these methyl groups on here, right? So it's a very clear correlation there where we go to this particular gas. More interestingly, though, is if you use ICP mass spec, so inductively coupled plasma mass spectroscopy, you can start to see that when you use, let's just look at the red here, dimethyl selenium, you get on the order of 20 elemental impurities in these systems. This is well below what you find in XPS, but not well below what can ultimately impact the electronic properties. So about 10 to the 11 atoms per centimeter squared, so that's guy right here. Anything above that is going to impact our electronic properties if we think about it from the silicon perspective. So silicon standards, we want to be below 10 to the 11 atoms per centimeter squared. So with using dimethyl selenium, we've got all sorts of stuff in here, right? So what we do then is we simply switch the precursor. So our MOCVD system allows us just to turn a knob. Well, not me, I'm a PowerPoint engineer, but my students to turn a knob. And we immediately, just by switching to hydrogen selenide, we get rid of, 10 elements or so. And then we are able to reduce a variety of these other elements that below the detection limit or below what's required. But we still have a few of these other guys over here that can have an impact, and that's coming from the way our system is actually set up. So, well, we've got stainless steel lining, etc., in our systems. So hydrogen selenide is extraordinarily corrosive. Selenium is extraordinarily corrosive. So we have to deal with that at some level. We have to understand that there's going to be some iron in there. And there's some various other things that I think partially depends on the person that's handling the sample, because, you know, as gross as it may sound, we all have a vapor pressure, right? So depending on what the concentration of that vapor pressure is, you can actually get variations in these films based on this. The other thing that we want to make sure it's clear is that there is a lot of competition for growing high quality materials, in the sense that we have to beat vacancies, impurities, grain boundaries, etc. You have to beat this, or understand this 2D substrate interaction, right? Because you can get all sorts of dangling bonds off the substrate. You can get interactions of this. I'll show some of this later on. And you have to really understand and be able to control these oxidative defects in here. Obviously, in PowerPoint, I can just erase them. But in reality, when we're doing experimental work, how do we really control this kind of information? Because it doesn't matter, not information, this type of material issues. And then the other thing is really competing with Mother Nature. So this is a phase diagram of MOS2, molybdenum and sulfur. All of the moly TMDs, moly-based TMDs, have a similar phase diagram, where this red slice here is MOS2. And what you find in this is that it is not a single line. There's actually a width to that line, right? So because there's a width to that line, that means that you being able to control the stoichiometry of your MOS2 or of any of your moly-based materials is going to be incredibly difficult. So you have to be very careful on how you grow these materials and understand them quite well. Now, the saving grace is if you're doing tungsten-based compounds, they're all line compounds. So you just see this nice clean line straight up here. There's no width there. The problem is if you're doing sulfur, selenium, or tellurium, very rarely are you growing the most stable phase of those tungsten-based or moly-based materials. So this is a nice little theoretical showing here. So the closer you get to blue, the darker the blue, the more stable. As it goes to white, you're becoming, you know, a lot less stable. You go to red, it's unstable. So you can look here at moly. Here's our, you know, oxygen, selenium, sulfur, tellurium as you go across. Well, moly oxide is the most stable. All these guys, the oxide is the most stable, right? So you're always going to be competing with this. So this is why doing in situ techniques in MBE or MOCVD or keeping things in a glove box are always really important, because, well, you take them out and you want to run them down the hallway to do something. Depending on the level of stability here, you're going to have to run faster. So that's why none of my students ever give me a sample. So let's move to epitaxy with all of these things kind of in our mind. So if you think of traditional epitaxy, you want to match the lattice of the substrate to whatever it is you're growing on top of it, right? So if you plot these couple of 2D materials here, over some substrates that you might think of in terms of the nitride, silicon carbide. Here's graphene. He's way down over here. Here's a sapphire up here. Naturally, you say, okay, well, gallium nitride, that looks pretty good because it's very closely lattice matched. And in fact, we've done a good bit of work on this. I've published a couple of papers in the last several years. You can get beautiful lattice matching to the gallium nitride underneath, and in fact it is epitaxial. You see that the domains of the 2D material grow very nicely on top of that. But interestingly enough, you don't have to just sit and look at this particular traditional lattice matched system. You can grow on sapphire as well, which is on the order of 30 to 40% lattice mismatched. And the reason is because of long range commensurability. So you can get on the order of 6 or 8 metal atoms in the TMD matching up with, you know, some odd number of aluminum atoms underneath. And so everything, even though there may be a van der Waals gap between the 2D material and the substrate, it still has to reduce its interfacial energy to as low as possible. So it's still going to want to rotate and orient in a particular way, as long as you have enough energy in the system to be able to do that. And I'll show that there is a limit to you being able to do something like this. All right, so 2D epitaxy. So we a while ago started looking at this. Let's say grow on sapphire because it's a crystalline substrate. SiO2 is awful for many reasons, but we're just going to stick with epitaxy. It's hard to do epitaxy on an amorphous substrate, right? Here's our as-received sapphire pre-growth, so AFM, beautifully smooth. We grow on it, we go, okay, well, what's all this hubbub about epitaxy? It doesn't look like any of these are oriented. And in fact, we go through several hundred of these domains, and we see that there's no real preference to orientation of one with respect to the other. They're just all over the place. So then we look back at some of the papers from the 70s, 80s, 90s, all of which were probably older than half the people in here, and said, okay, well, why don't we just anneal these things in oxygen or hydrogen? Because that's a pretty traditional thing to do with sapphire substrates. And in fact, when we did that, this is a little bit higher roughness than everything we have, but it shows a point that you can get these this nice terracing on the substrate surface, right? And in fact, if you look at this, here's the non-coalesced to a coalesced region. They kind of look like they're oriented there. And if you do that in this non-coalesced region, you see, in fact, that most of them are in one particular orientation or the other. They're either in the same direction or in opposite directions. It's because this is crystallographically equivalent, because it's threefold symmetry, to the substrate underneath. So I thought, okay, this is great. Why is this happening? So why do we have to anneal it? There's various different things. I mean, substrate polishing can cause damage, etc. But we wanted to better understand the surface a little bit. So we did some contact angle measurements in these systems based on whether the condition of the sapphire. So this big black square here is our sapphire. There's a water droplet there, and this angle that we're measuring here, the water droplet, tells us a little bit about the surface energy of the material. So the lower the angle, the higher the surface energy. So that means it wants to lower its energy, so you're going to get stronger interactions between that and the 2D material. And in fact, so this is as received, 1150C, 1250C, 1350C anneal of the sapphire substrate alone for 1 hour. You can see here at 1250C, it dramatically decreases in the angle, telling us that we've now done something to significantly increase the surface energy of that sapphire substrate. And in fact, what we do is if we plot nucleation density, alignment percentage, average domain size, as a function of unannealed all the way to this higher anneal, what we see is the nucleation density and the alignment percentage goes way up as we reduce our contact angle in this. So the higher the surface energy of the substrate, the better alignment, the better interaction we get with the underlying substrate. It comes back up here at 1300, everything drops back down. So, so relative surface energy, high-low. So we can then extend this. What I've talked up to this point was some powder vaporization of MOS2. We can extend that to MOCVD of tungsten selenide on sapphire. So this is, again, that same image over 1 centimeter square. So we have a tendency we try to look at the entire surface of this, not just small areas, to make sure that we actually have some statistics. And in fact, we say, okay, we've got our special sapphire now. It's annealed, it's beautiful, we're gonna grow on it. We grow at 650C, and what we find is when we do electron diffraction is this beautiful halo of stuff around our primary beam. That tells us that we have no orientation preference whatsoever. So immediately the concern was okay, well, we had epitaxy, but now we don't. We have a different growth process. And no fear, though. Well, the other thing to note is when we do TEM and STM, we find defect densities on the order of about 10 to 13 centimeters squared. So this is related directly back to our previous speaker on the CVT materials. But if we increase this temperature, add more thermal energy to the system, what we find is that, in fact, we can get some beautiful epitaxy. So we do our electron diffraction pattern, we get these beautiful spots on here. It tells us that all of our triangles, all of our domains, are now oriented with respect to each other. They're either pointed up or down, right? Because that orientation, it's threefold symmetry. So that orientation, you can't tell a difference in the electron diffraction pattern. The other interesting thing, but it does tell us that there's true epitaxy to the substrate. The other interesting thing is we saw a dramatic decrease in the defect density in TEM and STM on the order of about 100x in these material systems. So, so we were able to do epitaxy on this, but we needed higher temperatures to be able to achieve epitaxy. Now we can get it at lower temperatures on graphene, but graphene isn't always very exciting to grow on for people at Intel, for people that want to make devices out of this, because you just end up shorting your device. So lower temperatures can be achieved. It really depends on the lattice mismatch. It depends on the substrate that you're interacting with. But mostly what we found is we're on the order of 800 C or so for this epitaxial process. Okay, so so how do we get to these lower defect densities? So this is actually, this is on the order of about 10 to the 11 per centimeter squared. And this is, extrapolated from STM and STS, which can have a big error bar on it if you're not too careful. And what we did, I have to excuse this, but so this is how we grow our materials, right? So we bring it up to temperature, we let it sit at 500 C for a little bit. This is to get all the water vapor out and off the surface and everything. Then we take it on up to 800 C. We puff a little bit of higher tungsten in the system and turn our selenium on. Then we reduce the tungsten, let it sit in the selenium for a little while to ripen. So at this point you've got excess tungsten on the surface, you're letting it ripen and grow laterally. And then we turn the tungsten back on, you turn it off and it comes back down. You do STM, and it looks very similar to what we saw earlier in the STM. You've got bright and dark spots, very high density of defects in the system. However, if we let it soak, like I'm calling, so post-growth anneal in this particular case, and you just let it sit, after you turn the metal off, you just let it sit in the chalcogen. Now this can't be just any chalcogen because precursors matter, right? If you find that you're using these large ligand precursors, you can end up depositing a lot of carbon on it. So in our particular case, we're using hydrogen selenide. It's a very clean precursor, but it's also very toxic, and it took us a couple of years to be able to get around safety, not around safety. We worked with safety to be able to make it happen. I know. We worked with safety. So when we do this annealing process, what we find is we reduce the defect density quite dramatically again. And it's on an order of 10 to the 11 to mid 10 to the 11, depending on where you look in this process. But it was really key. All we did was just add another anywhere between 10 and 30 minutes of annealing in this process. I'm saying here it allowed us to heal the defects. I think what it's doing is it's giving more time for the tungsten to move around, to any excess tungsten on the surface to react. And we also do see a large number of selenium vacancies in these, and selenium double vacancies. And it's related to the interaction with the substrate in our particular case, because this is a very non-equilibrium process. Okay, so we get to this point where we go at epitaxy. So it's interacting with the substrate. We've reduced the defects by introducing a little bit more of the annealing. How does it work in terms of FETs? In this particular case, we're doing top-gated, but electrolytically gated FETs, because we have not put a lot of time into top gating with ALD processes and understanding that. So maybe we should send some to Aaron. What we found is orders of magnitude difference in the low temperature versus high temperature in terms of on-off current, and a significant improvement in the subthreshold slope in this particular case. And the other thing that we found is that our guys are in blue here, so depending on the contact, your FET mobility can change because there's contact resistance impact, right? But we were on the order of 10 to the 7, 10 to the 8 on-off ratio in these materials. So you can see here it's a good on-off ratio. And mobilities that are very similar to single domain with gold. So in this particular case, it's one large triangle, source drain. In our case, we've got many domains, and we're still able to achieve very similar mobilities. So we were happy about that, because that told us even though we've got some triangles pointing up and down where we can get these anti-phase domain boundaries, those are not dramatically impacting the transport in these material systems. The problem is if we look at this as grown and you look at exfoliated is still another 10x higher, right? When you look at the literature. So we wanted to understand what is going on in this particular case. Why aren't we, if we're doing such a good job of understanding epitaxy, why aren't we up here? And that really comes back to 2D, 3D interfaces. and what's happening at the interface. So we did a lot of work in TEM trying to understand, here's our tungsten, what's it doing on top of the sapphire, and it turns out there's this funny looking buffer layer here that we call. And if you do some EDAX of that, EDX, here's our high resolution stem, and here's our EDX for our selenium. What you see is that their selenium has actually come down into this buffer layer. So that told us that there's no tungsten there, there's no oxygen there, so our sapphire stops pretty abruptly right here, so that's why I'm just showing you. You can get more information in this paper if you want to in the supplemental. So we went through the various models to say, okay, what could it be? I mean, so they looked at these top two. We didn't really think that it was, we knew it was not a pure interface, and we knew, we had a feeling that it was not oxygen at the interface, so we obviously picked what the most stable selenium passivation was of the models that our colleagues were able to do. And when we look at this, what we find is in the density of states, in fact, you can see where the Fermi level falls. We get these peaks in the density of states, the Fermi level falling within the valence band edge, or a new defect state showing up here. So that can lead to some scattering. That can lead to some mobility reduction in the material. But I think more interestingly we found was when we did AFM. So here's topography. We picked a particular area, this mono, bi, and tri-layer. So you can see, it's hard to see those here. But if you do AFM topography and you match that with KPFM, which tells us a little bit about the Fermi level of the material, right? It's contact potential difference. So this is actually work function of the material. And you'll see that there are these stripes that go along. And it turns out the steps in the surface of the sapphire match really nicely with these stripes. You see this giant contact potential difference variation, right? So we've got nanoscale variation in the work function. It's all over the place. We wanted to understand, this kind of gave us an idea that it was with the steps, so we did some more TEM, and we said, okay, let's look at the steps. In fact, you get some of these nice layers here, but then everywhere there was a step in the sapphire, see here, 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 it's either nucleation of a 2D layer, or it's structural mixing of two different layers. So in this particular case, there's mixing. There's nucleation, et cetera. And it also turns out that there's a little bit of extra selenium in this particular case. So that told us that these steps are key for nucleation, but they also have an impact in potentially on the structure of the material. So we said, okay, let's try to understand a little bit what the impact of the transport is on these systems. So we made devices that were parallel and perpendicular to these zebra stripes. And in fact, when we look at the IV curves of this, what we find is that the threshold voltage is shifted quite dramatically for the parallel versus perpendicular steps. And you can see that here going to the positive. In addition, there's a large decrease in the saturation current here. Didn't quite get the saturation, but that's all we could follow, from what we could do with these electrolytic gating. So the real takeaway on this is that substrate terracing may be very important in nucleation and growth of these 2D materials, but it's also going to impact the transport properties of your system. And this is not unlike epitaxial graphene, so graphene grown from silicon carbide, where you have resistance differences on the order of 3 to 10x, whether you're going parallel or perpendicular to the steps. So this is a critical thing that continues to need some attention. And what we found is we're actually growing 3 to 5 layers. You can dramatically reduce this and increase the mobility as well as the performance beyond, but not with monolayer. It almost acts like a buffer layer when you're growing these. So the other thing is understanding what you have, claiming quality. I want to speed up. I have to speed up a little bit, otherwise Steve will be kicking me out. All right. So there's lots of claims, universal claims of my PL is great in this material, therefore the material was great. So you have to be careful about that. And these are just a few that I put up here just to talk about. There was a very strong emphasis on PL to say that the material was high quality, universally say that the material was high quality. So while those were coming out, we were also looking into this. And in fact, what we did was just change the substrate of for the 2D material growth, and not even change the chemistry, just change the orientation of the sapphire we were growing on. C-plane sapphire versus R-plane sapphire. And in the case, they've got different chemistries on the surface. One is more oxygen-rich than the other. The R-plane sapphire is more oxygen-rich. So we grow MOS2 on C-plane and R-plane sapphire. What we find is the R-plane sapphire has anywhere between a 50 to 100x improvement in the photoluminescence intensity. In addition to that, there's on the order of about a 30x increase in the lifetime of these materials. And this is now is on the order of what the claims are for the near unity, superacid treatment, et cetera. Right? But we did nothing with it other than change the substrate to grow on. So we wanted to better understand this because we can do now this on wafer scale if we want to. We grow 2-inch wafers in 2D CC, no problem. So looking at because I'm a material scientist, looking at the chemistry of this. So this is XPS, sulfur here, molybdenum here, R-plane at the top, C-plane at the bottom. This is post-growth, and what you basically see is that these all look kind of similar except the molybdenum oxygen bonding in the R-plane sapphire. So this kind of gives us a clue that the molybdenum oxygen bonding is much stronger in the R-plane sapphire, therefore that might be leading to this increase in the photoluminescence. So we wanted to verify that, and we annealed the material then post-growth. We took it back, we stuck it in sulfur, and we left it in sulfur at high temperature for an hour or two, and we were able to dramatically reduce this molybdenum oxygen bonding. And there's not a lot of other differences in this particular case. But what we found with this annealing is that our photoluminescence decreased. So it went back down. It didn't go back down all the way, but it did decrease. And we can go through this cycle of oxidation, sulfurization, and this peak will go up and down and up and down and up and down until it just completely quits on you because you've messed with it so much that it's done. So we said, okay, we think we understand where this is coming from. It's these oxygen defects in the MOS2 that are leading to this enhanced photoluminescence, somehow at very close to the same energy or at the same energy of your typical exciton binding energy you would see in MOS2, because we don't see a lot of peak shifts, which is very interesting in and of itself. We don't fully understand it, but we could clearly make this go up and down. So we said, okay, we have a way to control this photoluminescence. How does it impact the transport properties? So again, we make these top-gated FETs. And in fact, what we find, we go through subthreshold slope, mobility, et cetera. And even though our PL is increased by 50 to 100x, we get about a 2x decrease or a 30% decrease in mobility and subthreshold slope of these devices. So overall, electronically, you're actually degrading the material. Optically, you're enhancing the material. So be very careful when you claim that this universal high quality when you're trying to do these measurements. So when you take it out of the tube, you run it down to the Raman system and the PL system, you go, oh, the PL's awesome. Let's make some devices out of it. Be careful, because you might not always be really happy with what you see. And this is a good example of my students making lemonade out of lemons, I think. All right, so I want to talk a little bit about a pinch of salt. So again, like I had mentioned at the beginning, there are a couple of papers. Actually, this Nature paper by Ji-Won Park really popularized of salt-assisted growth. And of course, my students, several of them, decided to jump on the bandwagon. We started going along, and it never felt right to me because my doctor always tells me not to have salt in my diet. And then there was another paper that just more recently came out that just further pushed this effort of using salt. So we looked into it, MOCVD, dimethyl sulfide, and methyl hexacarbonyl, molybdenum hexacarbonyl. Apparently I needed my coffee after my lunch. And we stuck some salt in there up the furnace. Now clearly the salt is, you can change the position of the salt, so you can change the range of the amount of salt, sodium chloride, et cetera, you put in there. You can do the same thing with potassium iodide. What we found, in fact, was on nucleation, so this is a 5-minute growth, so it's a very short growth. We wanted to just see what's going on in this. And when we use salt, we see this very bimodal growth in here. When we don't use salt, we just see the standard nucleation and growth. That was very interesting to us. So we wanted to kind of understand this a little bit better. So we went ahead and we grew full films. and we stuck them in TOF sims to find out what is going on with this heterogeneous systems, what's going on to chemistry at the surface. And in fact, what we found, might be a little hard for you to understand, but basically this is a depth profile with TOF sims. So it can go on the order of a couple of angstroms, maybe 5 angstroms depth resolution, and tell you what the elemental composition is over a specific area. So it'll do mapping for you as well. So the brighter it is, the more salt, more sodium there is. We didn't really see any chlorine in this, but we saw lots of sodium. So the sodium signal here is pretty uniform. You can kind of see some little bit differences. But then you do one cycle of etching, which basically what you've done then is you've etched away your MOS2, and you look at it again. And you see here, then in certain regions, the sodium content goes way up. And then you do some more etches, and it starts to go down farther and farther until it goes away, right? What this tells us is that, in fact, the sodium is at the interface of the slow-growing triangles, the slow-growing domains when we grow them. And these are larger. These are these guys here. And there's nothing underneath there. So there's something about the sodium that works for a while on the outside of these triangles, outside of these domains, to help them grow faster. But then it stops. And you end up with sodium deposition all over the surface. So sodium at the interface of the MOS2. So this is heterogeneous. You've got sodium covering everything out here, no sodium underneath there, or very little sodium. So okay, well you can just transfer that and you can put it on SiO2, no problem. Okay, that's fine. So we did transfer it. Instead of on SiO2, we transferred it onto TEM grids. What we found is, okay, you put this general periodic array, that's particularly terrible looking on the screen here, but then there's this spot here, looks like a defect. Okay, that's wonderful. But in fact, if you look at the Z contrast of that, it is not empty. There's actually sodium that is in there in the lattice, which is clearly a problem when you're thinking about utilization of these materials and controlling the purity of the materials. So you get all sorts of things, material things that are going on that would change the properties of these materials, because you can imagine something sitting on sodium is going to act very different than something sitting on SiO2. So we did the FETs. We did top-gated FETs on the as-grown, and we did transferred and back-gated material. So in the transferred, the claim is you get rid of all the salt because you're using DI. It's a beautiful thing. They show XPS. There's nothing there. In fact, there is something there. The key is that you get a degradation in the off-state current by about 10x in this. And if you look at the mobility, et cetera, regardless of, these are very different techniques. You can't directly compare the top-gated because this is electrolytic gated and this is back-gated, right? So they're very different electric fields. So you have to compare them just amongst themselves relatively. So performance degraded when we use salt. But I think the more important thing is the fact that there's been 50+ years of research in the semiconductor industry to get rid of sodium and potassium, all of these alkali ions in the process. And now we've come along and we're specifically, we're taking gram mols Morton salt and sticking it in there, and we can't do that. So I'm sure there are lots of processes or lots of applications where it's sodium and these alkali ions can be tolerated. But if you're thinking about 2D materials for beyond CMOS, for high-end electronics, even potentially sensors, since I'm a doctor, I want to have you try a salt-free diet when it comes to these grows. So that's my opinion on this whole thing. All right, so tuning properties. We've looked at, now this is all salt-free, so we've gone, we're salt-free diet. We've looked at rhenium doping and niobium doping. And I'll just quickly go through this. It's the same process that I've been showing before, except now what we're doing is we're introducing rhenium decacarbonyl in this particular case, and it should be an N-type dopant. And in fact, when you introduce this rhenium decacarbonyl, and you can look at the paper here for more details because I have to go a little bit faster. You can map out with TOF sims again where your MOS2 is. These are just individual domains. They don't look like triangles because the resolution isn't all that great for the TOF sims in this particular case. But if you're able to see this, there's actually all these little specks here of rhenium that are in the same place here. So that tells us we've got rhenium located in the position where the molybdenum sulfide is. And XPS tells us there's these two little bumps here. So we get on the order, depending on the temperature of the rhenium decacarbonyl, what you find is you can introduce anywhere between 0.1 and 1% in these materials. Of doping, this is actually on the order of alloying, not just doping. If you think of silicon doping, you're in the parts per million, right, for doping and controlling these materials. But now what we find is that we get on the order of 0.1 to 1% to be able to do anything with the electronic properties. If we push this, what we find, we see these bright spots here where our rhenium is, or where we believe our rhenium is. We're calling it a defect point in here. There's a reduction in the band gap and a little shift towards the N-type. We make transistors out of this, and in fact, you can induce the rhenium. Here's pristine MOS2, looks normal. Rhenium, you can push it to where it's just starting to come down, so several volts. We can't go all the way because, again, this is electrolytic gating in this process. But this substitutional doping is very stable. But again, we have to always think about what's the overall environmental stability of these when we're adding in different atoms in these materials. Rhenium sulfide is pretty robust, and in this particular case, it seemed to work out pretty well where we could tune the properties from true Schottky to much more ohmic in this case. The other thing we're doing is niobium. So showing here in this particular case, niobium is supposed to be a p-type dopant, which is much more difficult to do than an n-type because MOS2 is not intrinsically n-type, but because of the way we grow it and because of that wide range of things, quite often it ends up as n-type simply because of vacancies and defects. So we use niobium pentachloride, and depending on the precursor temperature, so you can shift this curve here, which is an XPS curve of the valence band maximum. So where this guy comes down, so our Fermi level is here at 0, where this guy comes down here, that tells us where our valence band is with respect to the Fermi level, right? So what we find is as you increase the temperature of the niobium pentachloride, you can then push that valence band all the way up above the Fermi level in this particular case. So this tells us that we can very clearly introduce niobium into the system, substitutionally dope it into the material, and then be able to induce this to be degenerately p-type. So now you can start tuning MOS2 N-type to p-type on monolayer materials, not in bulk growth crystals. So it also dramatically reduces the low temperature optical defects that you quite often see in MOS2. It's very interesting. So this is at 5 Kelvin, I believe. So here's our exciton peak. You cool it down in a traditional one, you get this giant peak here that overwhelms everything. Almost every single person sees that, and most optical people hate us for it. But we've now doped this with niobium. We're not 100% sure what's going on, but the darn thing just disappears. So we need to better understand what's going on with this, but we were very happy with that. And the last example I've got in terms of the doping is the substrate impact of magnesium dopings, or manganese doping. So we want to make magnetic 2D layers, right? Can we do it in TMDs? Well, it turns out, if you look at the phase diagram, we should be able to put about 10 to 20% manganese in MOS2. We grow it on graphene, and we find that, in fact, we can get several percent manganese into MOS2, no problem. The problem, though, is when we go above about 2 to 4% manganese in the system, manganese sulfide is not a layered material. It's a 3D material. So now all of a sudden you've got this competition between what manganese wants to do and what we're forcing it to do. So you get, it's just like precipitation of elements out of the doping in silicon, et cetera. And in fact, what we end up doing is growing vertical structures, cube structures, all sorts of crazy things. But nonetheless, you can get a few percent of manganese in there. On the other hand, if you grow it on a traditional substrate, SiO2, sapphire, et cetera, we can't get any manganese in there whatsoever. And the point in this, well, so then we went back to our sturdy, the trusty TOF sims, and we said, okay, hey, there's manganese in there, because TOF sims can see parts per million, right? Even in some cases, parts per billion. So there's definitely manganese there. So again, mapped, here is our silicon, here's our moly, right? So where there's moly, there should be less silicon because molybdenum disulfide is on top of silicon in this particular case. And then we did rhenium, or sorry, manganese. You can't see it here, right? But there are actually spots in there. There are pixels that are colored. You'll have to take my word for it. And it turns out those pixels all are out here and associated with the silicon. None of them are associated with the MOS2. So it's very cleanly shown in that. You can see in this paper here. So what we think is going on is when we increase the temperature for growth up to about 800 C, we've got this SiO2 surface with water on it. It dehydrates. Now we've got these dangling bonds with the silicon, and that's where our reactive sites are. And it's actually more reactive with the manganese than with the MOS2. And we still have this interaction with the MOS2 with the substrate as well. That's a competition. So this comes back to this whole competition thing, right? We have all sorts of vacancies, impurities, grain boundaries, etc. So that's pushing us to dope these materials at a much higher level than what you would ever expect to do with traditional 3,5s or silicon. And it's because they're at the monolayer level. It's because you've got these interface interactions. You've got all sorts of things you don't have to deal with that you typically you don't have to deal with in the bulk. So we might have to get to the point where we have to we accept the fact that no longer can we do parts per million for thin films. We might have to think about growing multi-layer and getting it in, the tenths of a % range, which can have ultimate impact on transport anyway. Okay, so with the last 45 minutes, right, Steve? I'm just going to briefly go through this 3D to 2D very quickly, actually. So we've developed a process out of silicon carbide. So this is silicon carbide. We grow graphene. So it's sublime the silicon, and you come out and you make some graphene here. There's some beautiful images there, right? You can get this type of graphene has an interface here that is partially covalently bonded to the substrate. That's important for developing a new type of process that we use to grow new allotropes of 3D materials. So this dangling interface really wants to reduce its interfacial energy. And as a result, what happens is it will easily suck in whatever elements you're supplying to it to passivate it. In this case, it's hydrogen, and form another layer here. But you can do this with all sorts of different materials. So what we've done is, here's our silicon carbide, we grow our graphene, we introduce a few defects into the top of the graphene, and then we introduce an element such as gallium. That gallium then intercalates in between the interface. So it's a very high energy interface, it finds these defects, it goes in between. So it's like making your peanut butter and jelly sandwich, except you put the bread together first, then you stick the peanut butter in. Here's our jelly, nitrogen. So in this particular case, you don't only just intercalate one layer, but you can actually intercalate multiple elements in there. And you can do chemistry at this interface. So now we've created things like 2D gallium nitride. And this is known as confinement heteroepitaxy, CHet. If you do a year and a half to 2 years of optimization, you end up with things like this, where it's 2D gallium nitride. Here's our graphene. There's our silicon carbide. You do get quantum confinement effects in these materials, but that's not necessarily a bad thing. Here's high-resolution TEM and the structure of it. So it's actually a gallium-2 nitrogen-3 material instead of just gallium nitride 1-to-1. Graphene is key on this. When you use graphene, you always get this structure, this reconstruction. If you don't use graphene for this process, you just end up with gallium oxide like every other place on Earth. The confinement heteroepitaxy, or the quantum confinement effects come in when you look at the theory. It goes from 3.4 eV up to 5 eV, so deep UV, etc. And we verified that in fact this gallium nitride now is at 4.9 EV optically. So it's got some interesting characteristics of that. I'm actually more interested in doing this with indium nitride. You can see do the exact same thing with indium nitride. And the reason is because if we take our look at our band energy versus lattice parameter, we can take our indium nitride and we can move it. We have another knob to move it up through the visible for optoelectronics, which could potentially be some interesting things. The last little bit is we'll just stop here, right, and just stick our gallium in or our indium or whatever, right? So I was showing this to a bunch of physicists. This part wasn't terribly exciting to me, but when they saw that I did this with gallium, they were like, oh my gosh, we have to do this because gallium's a superconductor. So if it makes the physicists happy, I'm happy to go for it as well. So superconducting, push the superconductivity up potentially, to 5x or 5 Kelvin or so. So stop the gallium. Here's our 3 layers, 3 atoms of gallium, graphene on top. There's a TEM of the gallium itself. Vin Crespi did some modeling for us to show that these gallium layers are in fact not equally spaced, so the covalency changes as a function of layer thickness. And we've got TC on the order of about 4 Kelvin compared to 1 Kelvin for bulk gallium. So this is interesting from the perspective of a normal material scientist that does most everything at room temperature. It was a giant yawn for me, but from the physics perspective, they got excited, so I got excited. The other interesting thing is we're now looking at some of the plasmon frequencies in the, and it turns out that graphene's got this near IR or IR plasmons. Now you stick the gallium underneath there, and you have plasmon frequencies that are right smack in the middle of the visible. So we're very excited about that part as well. And you can do this with indium and tin and a variety of other material systems. So these are the materials that people have intercalated. These are the ones that we have done, the stars. And when we think about this, we think we can go to a whole huge range of different systems in here because we've not found an element that we can't stick in there. So we're pretty excited about that. So I'm going to go, there's a summary, that. Thank my group members. These are just various different pictures. We like to have a lot of fun in tie-dye t-shirts. Collaborators, a lot of them, and then of course the funding. So only 2 minutes over. Thanks, Steve.
Quick questions, maybe?
What's the business with the salt? Is that required for the MOCVD growth, or is it just?
Well, it's not required for anything. So the business with the salt was, that's right. Yeah, it's like an MSG. It really makes you feel good. No, so adding sodium chloride, potassium iodide, these different alkali compounds, apparently enhances the surface mobility of the metal that moly, tungsten, whatever that you're putting on the surface. And thereby, because of higher surface mobility, you get larger domains. So the key there was, can we make, the key for the community at the start was, can you make, hundreds of micron domains or millimeter domains, these kind of things. So this was a trick that people are starting to do now, and including my own students, right? But we've since moved away from it because of all of this, because we could not find an actual advantage. And then as soon as you look in the literature about alkali ions and CMOS technology, there's many, many decades of research on, just staying away from it.
After you etch the sapphire with hydrogen, is it still oxygen terminated?
So we typically anneal them in oxygen or in ambient. So there's a lot of oxygen around. So the stable termination of these are aluminum oxygen and aluminum, or aluminum oxygen and an oxygen. So it depends on the orientation, the crystal orientation in it. But we have no evidence that it is anything other than oxygen terminated in our process.
Okay, one more.
So when you're planting your atoms underneath for the graphene with the silicon carbide surface, so for your growth for the graphene, that's you have the silicon subliming out to those defects to give you the carbon-rich surface for those carbon-carbon bonds.
Mm-hmm.
What's I guess the trade-off whenever you have the silicon coming out and then the next stage of growth where you actually still want those defects for those whatever atoms you're implanting to go in, have you found any issues with that balance or any complications with the different rates and keeping those defects and actually having a uniform surface?
So the silicon doesn't just come out of defects. It actually comes out at the front edge of the graphene as it's growing. It's an erosion process, right? That's typically done at 1800 C. So we grow those in a separate chamber, take out the graphene, we walk over, and then we do this intercalation process, so where we introduce the gallium and that kind of stuff at 600, 700 C. So we actually have to introduce additional defects into the graphene to be able to get anything in there, because it's quite a low defect graphene that we're growing. And we find that it's very hard to intercalate anything when we're doing that because it's, supposed to be impermeable to everything, right? So we, take it out back and we beat it up and then we do the intercalation that way.
All right, let's thank